So you think gravity controls the universe? I mean, it keeps our feet on the ground and planets in orbit, so it's a pretty big deal, right? But what if I told you that on the smallest scales, in the weird and wonderful quantum realm, gravity is actually the weakest link? Today, we're diving deep into the three forces that truly run the show, the forces that build our reality from the atom up. Forget what you think you know, because things are about to get strange. Let's start with a force you're already familiar with, even if you don't realize it: electromagnetism. It's the reason your lights turn on, your phone charges, and why you don't fall right through your chair. At its heart, it's all about one tiny particle, the electron. When electrons are free to roam through a material like a copper wire, you get electricity. Simple enough, but here's where it gets interesting. Every time a charged particle like an electron moves, it creates a magnetic field. This beautiful dance between electricity and magnetism is what powers our modern world. But in the quantum world, it's even weirder. How do two electrons know to repel each other? How does a proton attract an electron? According to the theory of quantum electrodynamics, or QED for short, they're constantly playing a game of catch. They're not throwing a physical ball, though. They're exchanging something called a virtual photon. Think of it like a message carrier. One particle sends out a virtual photon that says "get away from me," and the other particle receives it and backs off. This constant, invisible exchange of messenger particles is what we experience as the electromagnetic force. It's the cosmic communication system that holds atoms together and builds molecules. Without it, chemistry wouldn't exist, and neither would we. Now, let's move on to the second force, the one that's a true master of disguise: the weak force. The name is a bit misleading. It's not weak in the sense of being feeble. It's weak because its range is incredibly short, confined to the inside of an atom's nucleus. But its power is immense. The weak force is the ultimate shapeshifter of the subatomic world. It can change one type of particle into another. This is the force behind radioactive decay. The most famous example is beta decay. Imagine a neutron, a neutral particle sitting inside an atom's nucleus. It's a bit unstable. The weak force can step in and perform a magic trick. It changes one of the neutron's fundamental building blocks, a down quark, into an up quark. In doing so, the neutron transforms into a proton, spitting out an electron and another tiny particle called an antineutrino in the process. This fundamental transformation is happening right now in the Sun, turning hydrogen into helium and releasing the massive amounts of energy that light up our solar system. The messengers for this force are heavyweights called W and Z bosons. Unlike the massless photon, these particles are extremely heavy, which is why the weak force has such a short reach. It's a powerful, but very private interaction, the secret engine of stellar fusion and radioactive change. Finally, we arrive at the undisputed champion, the heavyweight title holder of the quantum world, the strong force. And believe me, it lives up to its name. It is, by far, the most powerful force in the universe, over 100 times stronger than electromagnetism. So what does it do? It performs the most crucial job of all. It holds the very core of matter together. Every atom's nucleus, except for hydrogen, is packed with positively charged protons. Remember, electromagnetism, like charges, repel. So these protons should be flying apart with incredible force. The fact that they don't is a miracle performed by the strong force. But it gets deeper. Protons and neutrons themselves are not fundamental. They're made of even smaller particles called quarks. The strong force is what binds these quarks together, gluing them into the protons and neutrons that form the basis of all visible matter. The messenger particle here is aptly named the gluon. Quarks have a property called color charge, which has nothing to do with actual color. It's just a name for the type of charge the strong force acts upon, coming in red, green, and blue. The rules of the strong force state that you can never have a single colored quark on its own. They must always exist in combinations that are color neutral, like red, green, and blue together, or a color and its anticolor. This is called confinement. The force between quarks is bizarre. It actually gets stronger the farther you try to pull them apart. It's like a cosmic rubber band that you can never, ever break. So when we talk about the force holding the nucleus together, we're technically talking about a residual effect of this fundamental strong force between quarks. It's the unbreakable bond at the heart of reality. So there you have it. While gravity shapes the cosmos on a grand scale, it's these three other forces that govern the quantum realm. Electromagnetism, the architect, builds atoms and molecules. The weak force, the alchemist, transforms particles and powers the stars. And the strong force, the titan, binds the very heart of matter, preventing the universe from dissolving into a soup of quarks. Together, they form the incredibly powerful and intricate foundation of everything we see, everything we touch, and everything we are. The universe is far more complex and fascinating than just falling apples and orbiting planets. The real action is happening on a stage so small we can't even see it, directed by these three fundamental forces. Thanks for joining me on this journey into the quantum world. If you enjoyed this deep dive and want to explore more of the universe's biggest mysteries, make sure to hit that subscribe button and ring the bell so you don't miss our next adventure. See you in the next video.